Well, okay, within limits. So, yeah, so it's my pleasure now to introduce Thomas Aral. Next talk about quantifying quantum advantage through high-performance classical simulations.
Thanks for the introduction, and thanks to the organizers for putting together this nice workshop in this nice brand new building. And so, indeed, today I'm going to try to tell you more about how one can use classical simulations to understand what one can do or cannot do with quantum computers, and specifically today's quantum computers. And I will focus on two examples, one of which is rather pessimistic and one of which is more optimistic. And first, a little introduction. So I come from a company called Atos, whose main business is to fabricate supercomputers, one of which is represented here. So it's a big HPC system, high performance computing system. And the R&D lab where I work tries to understand how or whether one can use quantum coprocessors of the sort that are pictured here to accelerate some parts of computations. And for this, we make heavy use of classical simulations in the presence of realistic noise in order to understand whether a given algorithmic idea can work or not using noisy quantum coprocessors. And so I'm going to present mainly two topics. One, which is going to be quite similar to what Giuseppe talked about in his talk, which is trying to use classical simulation to reproduce here a very famous experiment by Google, although using a different technique than what Giuseppe presented. And then, and as you will see, the outcome is quite pessimistic with regard to the quality of current processors. And the second method, the second part will be about now, given the problems that we have, what tools do we have to try to find new solutions to make progress in this business? So let's dive into the classical simulation as a yardstick for quantum advantage. And I'm going to sum up here the game that Google defined to prove quantum supremacy. So what they did is they took a 53 qubit circuit. Why 53? Because 100 and they run a sequence of gates with random 1 qubit gates drawn at random here, and some pattern of 2 qubit gates, which I will go in more detail about later. And then what they do is that at the end of this circuit, they measure bit strings, and they look at the statistics of these bit strings. Now, if you had a perfect random quantum circuit without noise, what you expect to have is a perfectly chaotic state, which would have a distribution which is called Porter-Thomas, which is this green line. Now, if you have a perfectly random computer with very large noise, what you expect to have is that each bit string is basically uniformly distributed. In which case, each bit string has a probability 1/2 to the power n for n qubits, which means that what you expect for a completely noisy computer is basically a peak in this distribution instead of the Porter-Thomas distribution. And the game that Google set up is can we output bit strings here and see what is the distance between the best I can get and the random computer. That's roughly the idea behind Google's experiment. More precisely, they measure a given number, which they call the cross-entropy benchmarking, which is defined in this way. Here we have the sum over all possible bit strings, so there's an exponential number of them. For here you have the distribution that actually comes out of your quantum computer. So that's a quantum distribution, Q over X, for a given quantum circuit. And PU of X is the perfect distribution that you would have obtained if you had a perfect computer. So of course, in principle, you don't have access to this number because it's exponentially hard to compute. And you average it over several realizations of the random bits. Of course, you don't have access to this QU of X exactly because you cannot really have access to the full distribution. You don't have an infinite number of samples. So the way that Google computes their cross-entropy benchmarking is by doing a statistical average over the samples that they draw from their quantum circuit. So that the number that they want to compute is such a number where they repeat the experiment n samples time. And for each bit string that they get, xi, they need to compute the perfect, the value of the probability, the perfect probability for this given bit string, which is exponentially hard to get. But I will explain to you how they do it and how one usually compute such probability for classical simulation. And of course, they want to compare the XEB they get with their quantum computer and the amount of time it takes them to get this XEB with the same classical task. Namely, suppose I have a classical simulator that my task is to output n samples bit strings with a quality factor which is equivalent to this XEB in a time that is reasonable with respect to Google. And the claim of Google is going to be that it takes much longer for a classical computer to do this task than for their Sycamore processor. And now let's try first to imagine what we expect in terms of this quality factor XEB. And there's a very important law that you can have in mind, which holds only for random circuits, which is that if you perform operations on a quantum computer, it could be gates or measurements or initialization. So that's what I call FK. So these are small operations. And if you want to get an estimate for the final fidelity of the state that you compute, there's a very simple law, which is a product law, where you make the product of all those operations. So if we do this game, if we play this game for the Google experiment, so they have a 1 qubit error rate of 0.16%, and they have 1,116 such gates, and so on and so forth for the 2 qubit gates and measurements. And if you do the math, you get a final fidelity of 0.15%, which is very low, but that's what this estimate gives you. Now, a second important result is that for depolarizing noise, it turns out that this XEB that they designed, which looks a bit strange, is in fact the same as the fidelity for depolarizing noise in random circuits. So that XEB can be seen as a proxy for the fidelity that you get. And indeed, the XEB that Google gets, in a way that I will come back to later, is 0.2%, which is pretty similar to the back of the envelope computation that I just did. And just as a remark, this is a very low fidelity, which gives us already the level of confidence or the level of optimism that one should have with this processing. So after a couple of gates, you get very low fidelity. So there's so at the moment that tells you that it's going to be hard to have quantum advantage with such circuits. Okay, but now let's try to focus on how did Google measure this XEB, knowing that the hard part here is to compute the probability, the a priori probability of a given bit string after performing a quantum circuit. And for this, I'm going to go a bit more into the details of how one simulates a quantum circuit on a classical computer. And I'm going to view basically all simulation techniques in a unified framework using tensor networks. So our goal is to compute such a probability, which is just a scalar product of a bit string with the wave function. And if I now rewrite the wave function as a unitary representing my quantum circuit acting on the zero state, that's what I get. So I want to compute this number. And I'm going to manipulate tensors, or matrix, for instance, is a rank 2 tensor, a vector is a rank 1 tensor, and this box here with 3 legs is a rank 3 tensor, and a matrix multiplication can be represented as here, this drawing here, where I just draw a link between the 2 matrices, which represents an internal summation, like in an Einstein summation. And contraction is just putting together 2 of these boxes. And it turns out that a very important result in this contraction of tensor networks is that the order of contraction matters. If I look at a tensor network A, B, C, D like this, a naive way of contracting it would be to sum over I, J, K, L at the same time, and a kind of big for loop. And that would give me a complexity of N4, N to the 4. If I now do a more clever contraction strategy, what I'm going to do is use temporaries, basically. So I first contract A and B, that gives me A tilde, then A tilde and C, that gives me A hat, and then I contract A and B. So at the cost of having stored some temporary tensors, I arrive at a complexity of N to the 3. So that's a trivial result of tensor networks, but it's very important. And why am I talking about tensor network is because, in fact, computing what I want to compute boils down to seeing my quantum circuit, for instance, the Hadamard C0 as a tensor network. So basically, I can rewrite, so each gate is a box, the starting state is also a box, and also the string that I want to measure can be represented as small boxes. And so all I have to do if I want to compute the probability Px is to contract this tensor network. And so very important note here is that if I have a box here with, let's say, 3 legs, if I want to compute the storage cost, I just do the multiplication of the size of each leg with each other. So I do here 2 by 2 by 2, that's 8. So for n qubits, this polar wave function is 2 to the power n if I don't do any tricks. And in fact, we can see all classical simulation strategies as a contraction of a tensor network. So for instance, there is one which is the most straightforward one, which is usually called the Schrödinger type of quantum circuit simulation, where you basically contract in the time direction. So you first take your initial state and you contract the first gate. This gives you the purple box here. Then you contract the second gate. This gives you the purple box here. Then you contract the third gate and it gives you the purple box here. And once you have this purple box here, which is very heavy to store because it's 2 to the power n, then you can compute, what is the value of this box for the entries x1, x2, x3. And I get the number that I want to get. So the cost is very expensive because it's proportional to the number of gates because you do gate by gate. It's exponential in n, and it's also exponential in n in terms of the storage cost for the reasons that I said. The advantage of this method is that at the end of the computation, the box you get here, the purple box, has all the amplitude. So you can ask for all the amplitudes. But that's the price of storing everything. A second strategy is called the Feynman strategy, also called sum over paths, which basically consists in doing the naive contraction strategy where you write out all the different indices here, the internal indices, and you write this xu0 as a big sum over so all the internal indices. And then I just wrote what it means for the different boxes. And so what you do is a big for loop on these indices. And so as you can see, this for loop is very large. It's actually exponential in the number of gates for a fixed bit string. But the storage cost is very nice because for one bit string, you just do this sum, you obtain the final result. Of course, it has a price. You do it one amplitude at a time. So if you want all amplitudes, of course, you have to multiply by the number of amplitudes that you want. And then there's a final method, which in fact encompasses all of the methods, which is a general tensor network contraction strategy, where you still take your tensor network as a big, your quantum circuit as a big tensor network. You try to find the optimal contraction strategy, which in practice you cannot really find because it's an entry-hard problem. But you find a heuristic, you find a good contraction strategy, which is neither this one or this one. So it's something intermediate. And then you contract the tensor network using, let's say, CPUs or GPUs or tensor processing units that one sees through the developers. And the interesting thing is that the complexity of doing such a contraction is the exponential of something called the tree width of the underlying graph. I won't enter the details, but you can have in mind that the tree width for a graph which is a rectangle is roughly speaking the minimum of the depth, so the number of gates, and the width, the number of qubits of this tensor network, roughly speaking. So it gives you an idea of if you have a very long circuit, you're going to contract first. You're going to contrast more in the horizontal direction. If you contract in the vertical direction. And here again, you get the amplitude one by one. And so in order to do their computation, Google used the third strategy, but since it's scaled exponentially with the tree width, and the tree width in their case is something very large because they have a very large number of gates and very large number of qubits, what they did is a further trick where they said, how about simplifying our circuits by removing some gates that we don't like? Well, why don't they like it? Because if they remove them, then they have a much simpler tensor network to contract and they can actually do. And it turns out that despite this quite, if you say, so quite gross trick, the XEB that they get with the simplified circuit is the same as the one that they get with the hard circuit. And that's what they show on this plot here, where they plot the fidelity for the three circuits here, the full circuit and some simplified circuits, and you see that the points are on and off. Then what they do is that, so they check that for small circuits it works. So here they're in a regime where they can actually do the red circuits. And then they go to the regime that they like, so the depth of their random circuit and the width, so the 53 circuits. And then there they cannot do the red computation anymore, but they can do the blue and the green, which are the simplified ones, and they get the final number here called. So that's how they do this simulation. So you have to believe that the red point, if you could do it, would be here. So that's quite reasonable. The checks and now, so then Google claimed that if you wanted to do such a task on a classical computer, you would need 10,000 years instead of the 200 seconds that it took them to sample on the chip. And where this estimate comes from is essentially from the second approach that I presented, the Feynman approach, where they use a very important property, is that in the paths here that I mentioned on the previous slide, so here, I could choose to sum only a fraction f of the paths instead of all paths. And there's a property that tells you that if you sum only a fraction f of all paths, then the fidelity of your computation is f, and that works only for random circuits. So if you want to compute how long it would take you on a classical computer, what you have to do is compute the time it takes for one path, and that they did actually for one path. They took a really large supercomputer in Oak Ridge to compute the time of one path. Then they multiply by the fidelity that they measured, so this 0.2%, and then they multiply by the number of paths that they should do, so the full number, total number. And what they get is 10,000, and that's on this basis that they said, look, it took us 200 seconds, it will take 10,000 years on a classical computer, so we're done to 2026. And of course, now the question is, can we close this gap? So there has been several attempts to close this gap. A few days after Google's announcement, some people at IBM said, with a Schrödinger-like computation, I could do the same thing in about 5 years if you give me a large enough route. But they didn't do the computation. That's another which mixes Feynman-like basically what you do is that, for instance, in this circuit, you can open a line and you keep this index fixed V2, and so that the amplitude is a sum over V2. So you put the index V4 on this V2, and then contract the tensor which are simpler than the full tensor network. In that way, we can actually parallelize the computation over the values of V2 and get the result. So it's a kind of trade-off over of CPU and storage cost. And here with this computation, these authors showed that you can go down to 20 days to do the computation in the class. And then other people in China said that using GPUs, you could reduce further this to 5 days. And the last author is also used non-GPU, very large So the question is, now I'm telling this to you. So it looks like Google's claim now is defective, and so why should we do something? Well, the reason is that all these methods relying on tensor network compression are scaling exponentially with the number of qubits and the number of bits, which means that if Google adds 2 qubits or 1 layer, these methods don't work anymore. They don't scale. And what I'm going to show you today is a method that scales with the number of qubits with some limitations. For this, we're going to leverage an important quantity that other methods don't So in all previous methods, what people did was surrender fidelity by summing fewer Feynman paths. So when they lost something or they threw away something was by not summing all the Feynman paths. Here, the idea is going to be using entanglement, and I'm going to take a very simple example. So if you have a product state, so non-entangled state, the tensor network that represents the wave function is no longer a big box but 3 boxes. If you have an entangled state, something that is weakly entangled, you could use a representation for these three boxes, factorize it, product here, and then the idea is that if you give me a given matrix, a given general state, I can cut it in two. I can factorize it in this form by performing a singular value decomposition, which is a well-known algebraic operation. And the key thing is that I can also choose to compress this state by truncating the singular values in this SVD. And this is akin to a projection to a lower rank state. And the key result is that the fidelity of this operation, the fidelity of the truncation, is basically related to the area between the square, so below the square of I can compute the fidelity of this operation very easily, and therefore also get the fidelity of my full computation by doing the product of my different fidelities. So it's very easy for me to control what level of quality I have in my simulation. And so now let's look at how it works in practice. So the way it works, that has been presented a long time ago, is so let's take a problem. As you know, so the first state 0, 0 is a product state. So here I get the big box here, just three boxes with no link because they're product states. And now I apply my first gate is a 1-qubit gate, so there's nothing to do. I just want to contract it, and I still get a product state form. Now I have a 2-qubit gate. I contract it with these two gates, and what I get is a box here. But this box here is no longer in MPS form. So what I need to do is cut it or factorize it using SVD. That's what I do. I factorize it, so I go back to an MPS form, and then I compress if I have a bond dimension, which is too large, and that costs me. Then I can apply my other gate. I get this. This is no longer MPS. So I have to cut the box, and I get a second format. So the final fidelity of my computation here is going to be the product. So this method in theory works, but the fidelities that we get by doing this simple plain vanilla MPS simulation is too low. And so in the work that I wrote here, by basically, instead of taking a plain vanilla MPS with 6 boxes here, they took, okay, let's have like a Schrodinger-like simulation for this box and for this box, and we just have one link, one tensor. So they group some of the tensors together. And so that has a very nice outcome. Or upshot, which is that, so if we have qubits, let's say 6 qubits, and I want to apply the 2-qubit gate between those 2 qubits, then this 2-qubit gate is going to act on this tensor here. So I can basically contract this 2-qubit gate here, and I don't violate my group MPS form. So I don't have to do any compression step. Whereas if I do a 2-qubit gate here, and the 2-qubit gate acts like this. So when I do the contraction, I get a big vector, and I need to cut it, and cutting constants. So it means that for most of the gates, or all the vertical gates, this is free. I have a fidelity which is 1 for this operation. So that at the expense of storing bigger tensors, because these tensors I have a much better fidelity, and that's what they propose in this work. And they improve fidelity by quite a lot, but it's still not enough to get a Google fidelity, which tells you something about the fact that despite the low fidelity, it's still a very. And so we now come with a new idea is in order to really reach Google's fidelity is that we need to adopt a triply hybrid strategy where we mix the Schrodinger, tensor network, and MPS ideas together. So what we did in the previous, what the previous work did was I applied gauge here. Instead, what we do in this study is that we apply several layers of gates. So that's what I represent here. I start from a grouped MPS on the left here. I apply several layers of gates, at least 4 gates. So I construct the tensor network the next layer of gates. So there's k layers of gates here. And now what I'm going to try to do is can I find the group MPS that best approximates this small tensor network? That's the game that we're playing. And there's a very well-known algorithm to solve this problem, which is called density matrix renormalization group, DMRG, which, so the name is a bit strange, but it's there for historical reasons. But basically what it does is that it solves this problem. It tries to find, to optimize the fidelity of the MPS here with respect to the target state. And so it tries to maximize the overlap here of my tensor network corresponding to the k layers of gates that I added with an MPS. So it tries to find the tensors M1, M2, and M3 such that the overlap is the largest. And for this, what you do is a variation principle, basically, so you try to find the values of the tensors that make this quantity stationary. And what you find is a very nice result that comes from the canonical that, for instance, if I want to optimize this tensor, I will find the optimal tensor by fixing M1 and M3. So it's a local I'm not going to find the optimal in that sense. I find that the optimal tensor is proportional to basically the tensor network where I removed the tensor, which is a quite uniform. And this itself is a tensor network. So what I'm going to do is I apply my gates, and if I want to get the best tensor here, I just have to do a small tensor network contraction. And here I'm going to use the tensor network contractions that I mentioned previously. And so let's take an example. So if I want to contract to get the optimal tensor here, I have to do this contraction. And for instance, what I can do is contract first here, and here, and here, and here. So you get bigger and bigger tensors. And then at the end, you get your final tensor. So there are many strategies and very simple contraction strategies. But of course, the idea is that you want the number of layers not to be too large, because in the limit where the number of layers is a full circuit, we go back to the previous tensor network strategy. So here we add a few gates, then we contract, then we add a few gates, and we contract, and so on and so forth. And of course, here we do so-called DMRG sweeps, namely that we fix M1 and M2 and M3 and compute the best M1, then fix M1 and M3, compute M2, and we sweep when it converges. I have data. Okay, that's what we do, and now let's turn to the results. So first, a reminder, so in the experiment, the fidelity is the same as the cross-entropy benchmark. There's a very strange result in some ways that in our method, the cross-entropy benchmarking is actually the square root of the fidelity. You might say it's strange, but in fact, if you go to the chaotic limit and you do an equal computation, we can actually show that this holds, that the fidelity is 1/2 to the power n if you go to the chaotic limit, and the cross-entropy benchmarking is actually 1 to the square root of 2 to the power. So this relation is already, and it turns out that in our simulation, it is also the case. So here we did computation for smaller number of qubits, small but not too small. You see that we went up to 6 qubits using the machine, which is a machine we have and sell at Atos for simulating classical quantum circuits with a classical machine. And here we can show here that first of all, let's look at let's compare on this graph here the product of operation fidelity, so product of f, which is this dashed line, and the full fidelity f. And as you can see here, until I go to very large f, the product law holds. So it's just what I was telling you, f is a product of f squares. Then the second thing that we learned is that here I can compute it exactly because I have a classical simulator for 25 qubit. I can do it on my computer. And I compare it to the square root of f, I'm roughly on top. And you can see that this trend is true for all the curves, that XCB and square root of f is on top. So that's a law that is quite clear here. Of course, for Google Sycamore, 54 qubits, here we took one more. It was simpler to do. We cannot compute the exact fidelity because it's too large computation to be made on a classical computer. But we can nevertheless have the product law, and here we can have access to the square root fidelity. Okay. And basically the main result that I'm going to show is the following. Here, what we are drawing is the error per gate instead of the fidelity. So I just took here the final fidelity and did 1 over the number of 2-qubit gates. And then I draw the error per gate in percent as a function of the bond dimension, which is the compression level of my MPS. So what you can see here, so first let me comment on the gray line. So the gray line is basically the level that Google could reach in terms of XTB. So that's what we have to beat. We have to beat 3%. And if we beat 3%, basically we won Google. As you can see, for a small for small bond dimensions, so when I compress a lot, I'm above. So my compression, I throw too many singular values away. But as I increase the bond dimension, I reach a point here where I go into the gray area. And which means that in this area, I can basically output results with a fidelity which is better than Google's fidelity. And the time it takes to do this computation is a few hours. So it's not 200 seconds, but as I will argue, it's not a big deal. And let me do a comment. Here, as I mentioned, that in the Schrödinger simulation mode, you could have all amplitudes at a time. That's something called strong simulation. Here, when you do a simulation where you compute one amplitude at a time, that's something that we called closed simulation, because you close your tensor network and then you contract it. And it turns out that we could do both with MPS. But here we use a closed mode because it allows for a lower error rate. Why? Because basically we can contract our tensor network from the left and from the right. So from the left, starting from 0 state, and from the right, starting from the bit string whose amplitude I want. And the reason why I have lower losses is that both states here, x and 0, are product states. So when I compress from these product states, I start from low entangled states, so my compression is not harmful. Of course, when I get to the middle of the circuit, then I get something which is quite which is quite costly. And in fact, the final few layers, which is this parameter D2, is something where we do the contraction exactly with a tensor network. So we do a few layers with MPS contraction, and the last layers we do it with a full tensor network contraction, which explains to you why I have two curves here, dashed and not dashed. So not dashed, so the solid lines here is when I have really only one layer that I contract exactly. And here, D equals 3 is when I have 3 layers. So it's more costly, but it gives me better results, which is what we expect. And now a final remark is that you might ask me, but is it enough for me to be able to compute one amplitude and then sample like Google did? Because this is what I want to reproduce. And in fact, there's a recent work by Bradley et al. that show that if you have one amplitude, if you're able to compute one amplitude, basically you're able to do weak simulation. So just draw samples from your simulation, which is not obvious for MPS. It's obvious from the method for the method that Giuseppe presented, that you can sample bit string, but for MPS it's not that obvious. So it's quite important. Although in our case, because the distribution is chaotic, Metropolis Hastings sampling would work very well, because for a chaotic distribution, you can show that the acceptance probability would be 70%, which is it's enough for Monte Carlo. Okay, and now an interesting result is that if you change a circuit and take a simpler circuit, the error rates that we get in our method are much lower. So here, this is a supremacy sequence where you see there's a pattern of 2-qubit gates. And if we take another sequence, which is easy, why is it easier? You can see here that there are here less 2-qubit gates to cut here. So here you always have top, top, top. Here you have more time where you don't do anything, where you don't entangle. And when you look at the curve here, it's much lower when you do this simulation, which just tells you that Google really designed a circuit that builds up entanglement the fastest that you can. And if you do something simpler, then classical methods have are easier to use. And if you now use a useful sequence, so I say useful because I'm using here a QAOA-like circuit. So useful, I don't know yet, but let's say it's QAOA is used for solving useful problems, although maybe not at the moment in a way that is more advantageous than classical computers, but nevertheless. So this is such a circuit, and then if we use this circuit and compute the corresponding error rates, because this circuit entangles the state in a much slower way. And this is more or less what Giuseppe said also about RBMs being more efficient when dealing with QA/UA. We have error rates which are much lower, meaning that if Google is to do QA/UA on their chip, you'd better use a classical computer. And now an important property of this method is that it scales, and that's a very important property. So here what we did is now we fix the depth and we increase the number of qubits, and we look at the error. And here there's a result here which looks pretty counterintuitive, which is that the error increases as we might expect, but it saturates. And the scaling also is not that hard, right? So as you increase the number of qubits, here it's a linear scale. The error increases, but it's not an exponential increase. I will come back to it why we have this saturation, but when we see this data, we're quite happy because it means we could simulate Google with 250 qubits. Now there's another remark. As you increase the number of gates, the cross entropy benchmarking decreases because of this product law, which for us is not a problem as classical simulations, but for Google is a problem because if you have a very low cross entropy benchmarking, if you want to resolve it and really say it's 0.2%, you need more samples because you have to beat the statistical error. And so that means that in practice, you need to increase the number of samples, which increase your simulation time. So the 200 seconds of Google will be increased if you go to larger number of gates. So that if you want to compare to a fixed XCB or fixed number of samples, or fixed 200 seconds of Google, you need to fix actually the n times d, so the number of qubits times the depth, because then you have a fixed XCB. But then for us, if we do this in our method and we fix ND, then the error rate actually decreases. Okay, and now let's try to understand why we have this trend. In fact, you can actually compute the optimal error rate after an SVD if you take a random quantum state, a Porter-Thomas distributed state, and you do an SVD and you look at the singular values. You can actually compute this epsilon opt. And if you now compare this epsilon opt with what we actually get and what you would get if you do here an SVD of your state, you see here that we actually have an error rate which is larger when we get to the chaotic region, when we have a large number of gates. But roughly speaking, epsilon opt is a lower bound for our error rates. And when we look at the behavior of the epsilon opt at fixed d and increasing n, you see that it saturates to log 2 over d, which is more or less what we observe here. So of course it's a lower bound, so you would get a curve which is more or less parallel to this curve, but that explains the behavior that we see here. Okay, so that's the conclusion of this first part, where basically the outcome is that we can win Google's game and by leveraging 3 different simulation methods. And here, let me mention that we really use a very simplistic implementation for the tensor network contraction. So we could be much faster, but we didn't want to spend time. Important comment is that one has to be aware of the large Hilbert space fallacy. You hear in a lot of quantum computing talks, or the people say exponential and therefore classical computers are dead or whatever. Of course, it's not true, because usually what classical computers do is that they leverage the fact that you're dealing with a portion of the Hilbert space which is very small because of area laws or something like that. And of course, you could also try to beat Google at its own game by using neural networks. So that's the work that we were just presented. We did try a bit with RBMs. Well, so far, as you said, with random circuits, it's quite hard. But also, maybe a more positive outcome of this study is that qubit quality is crucial. For our method, if Google were to divide by 10 their error rates, then we would have a hard time. Because as you can see, our curves here still tend to saturate when you increase the bond dimension. There's a level where we cannot go lower. So at some point, if Google goes below a certain threshold, then probably the method will have a hard time. So that's where the exponential comes in this method. The exponential is in the fidelity that you can reach. It's not in depth, not in number of qubits, but in the qubit quality, which is quite interesting because it could be that the threshold that I have to reach for us to be dead, or for this method to be dead, is maybe close to the error correction threshold. Who knows? And also another thing that we can learn from this is that this cross-entropy benchmarking fidelity has some flaws. It's not a scalable measure. They had to play all kinds of tricks in order to compute it, and so they did this simplified circuits and so on and so forth, which works only for random circuits. And it also does not really tell you about the quantity, the ability of quantum computers to perform a useful task. So that I invite you to check an alternative benchmark that we propose at Atos for Q-score, which measures the ability of a quantum computer to solve a useful problem, which is called the Maxwell problem, using QA web, or annealing or whatever. So now in a second shorter part, I'm going to talk about. Now, so given this quite pessimistic result. In terms of time. Yeah, I think, yeah, that's good. Yeah, exactly. Yeah, that's perfect. So here, I wanted to show you more on the silver lining side, how classical simulation can be leveraged to test advanced quantum algorithms. Of course, this week we heard a lot about VQE, so I'm not going to spend time on it. So we've all heard that so VQE is a hybrid algorithm where you compute the energy, and the energy is decomposed in a sum of terms, each of which has to be computed using a number of shots, which give you a statistical variance, epsilon statistical, which is one of the square root potentials of central limits here. So that the VQE complexity can be summed up as the number of iterations, so the number of back and forth between CPU and GPU, times the number of shots, times the number of terms. And we heard a lot of talks this week that told us how you can better group the terms, how you could leverage or change VQE to projective methods and so on and so forth to try to have a better complexity. And there's another problem of VQE, so because this complexity holds for perfect computers, but if you add noise on top of that, you also have an intrinsic epsilon, an intrinsic error that comes from the quantum noise. So to decrease number of iterations and epsilon intrinsic, we heard a lot about adaptive algorithm. And so I'm not going to take a lot of time to talk about it a lot, because we heard nice talks about it. I'm going to flash, though, a couple of software tools that we provide in order to do this in a very easy way. So if you want to get started and you want to have a way to implement it. What I will spend a bit more time on is this idea, which is how can I use a smart single orbital basis to have better results in VQE? And this method is called natural orbitals, natural orbitalization. And so that's something that is probably familiar to the chemists in the room. So our goal in VQE is to minimize this quantity here, where psi and h are implicitly expressed in a given basis, which is the molecular orbital basis or whatever. So these indices P and Q actually refer to a given orbital phi of P of R in real space. And of course, we can freely change the basis by doing a unitary transformation. And of course, this is completely equivalent. The psi and the h are just expressed in a different basis. But we can exploit this freedom. Although equivalent, these bases are different, for instance, in the terms of the sparsity of the representation. So I took a very simple example. If I have a state 1, 1 in the C dagger 0, C dagger 1 basis, then if I have a rotating basis like this, the state here is much more complicated. And therefore, the overhead to prepare it on the quantum computer is different. So that what we can do is try to find a clever basis. And one clever basis that we propose is called natural orbitals. It's defined as the basis that diagonalizes the one particle density matrix, which is defined in this way. So supposing you have the solution, which we don't have, you can compute this matrix Dij. You can diagonalize it, find a unitary transformation that diagonalizes it, and then go to this basis. And it turns out that it's well known from quantum chemistry that this is the basis in which the ground state can be written with the least number of Slater determinants. And hence, it's also the basis in which the preparation circuit is going to be the simplest. That's the intuition. And indeed, that's what happens. And here we can check that. So let's look, for instance, at this noisy simulation here. So here I have a long ansatz and a short ansatz. The long ansatz is supposed to give better results. And we actually, the long ansatz, which is called LBCA, actually gives better results. That's what you can check on the left here. Usually you converge faster and it gives a better energy. And the short ansatz doesn't necessarily give the best result because it's short in the absence of noise. But now, if we increase the level of noise, if we look at the dashed lines, the long ansatz is basically killed by noise. So the plateau here is very far away from the perfect energy. And the short ansatz is slightly better because it's short. And that's in the original basis. But now if I turn to the natural orbital basis, you see here that the solid lines here are systematically below the dashed lines. So that if I go to the natural orbital basis, I have better results, and that's basically for free. Of course, I have treated a bit in the sense that the ground state is not known. The exact ground state is not known. So what we do instead is that we do a procedure that we call natural orbitalization, where we compute an approximate 1 RDM with whatever we have. So the first VQE shot. We do the rotation to the approximate NO basis. We get a new approximate ground state, and so on and so forth. So we do it in an iterative way. And it turns out that this iterative way does work in the sense that here on the model, which is an Anderson iterative model, which people like to use in embedding techniques, it's a strongly correlated model where we check here for several correlation levels. U equals 0 is no interaction, and U equals 2 is quite a large interaction. The mod transition is at U equals 3 or something. You can see here that, so that's the NOization step. So the step in this iterative procedure, you can see here that we do go towards the same result as what we would have gotten had we cheated, as I showed in the previous slide. So this iterative stimulus. And we apply this method within an embedding technique that I won't have time to talk about, but you can check it out in the paper. And now in the final 5 minutes, I'm going to talk a bit about the software tools for VQE. So you might see that as an advertisement section, but it's actually not. I mean, it is, but I'm a numerical physicist, and I know that tools are very important. And having nice tools to test ideas very fast is very important. And that's why I'm quite convinced that although it's advertisement, it's also useful. And so the final results that we obtain using those tools are, for instance, you can do adapt VQE, and on the quantum learning machine, you can actually test very large molecules and so go beyond test cases. So here we really do hard work with quantum chemists to, for instance, test LIH with 20 qubits, so in a quite large basis set. Okay, so I won't go back to it because we had several talks about adapt VQE, but it's just to tell you that with the tools I'm going to present, you can really go to very large number of qubits in a way where the code still is manageable. Okay, if I want to write a VQE loop, I need a quantum chemistry code. This, everybody has their own chemistry code. What is important is that at the end, you get your 1 particle and 2 particle integrals, HPQ and HPQ-RS, and maybe the RDM if you want to do some active space selection. But that's up for the user. You have PySCF or Psychology or then you need to go from fermions to qubits. So you need to take your Hamiltonian H and choose a clever way to go to qubits, so either Jordan-Wigner, Bradley-Kutaev, parity, or others. We heard about others today, yesterday actually. And you could do active space selection based on the density matrix, for instance, if you want to select your active space. Then you construct your ansatz. So for instance, in the case of UCC, you could construct a cluster operator based on some constraints of conserving some symmetries. You could also choose an initial guess to start your UCC, for instance, by using Müller-Pesse second-order perturbation theory. And then you need, for instance, to trotterize your circuit, but of course, there are more advanced methods. And then you have a quantum job. So your job is basically a variational circuit and a Hamiltonian whose energy you want to minimize, and this is what VQE is supposed to do. And what you have is access to a QPU, either a true QPU, IBM Quantum, Google, Rigetti, or a noisy simulator, which has some Gauss operators, some spam errors, and so on and so forth, or a perfect simulator of the ones that I talked about in the previous slide. The problem is that the true QPUs, they only receive jobs which can measure along the z-axis. That's the Stern and Gerlach experiment that we heard about two days ago. And so that's the only thing they can do, and they can also only receive circuits that have native gates. So they can only receive gates that they know how to do with the connectivity that they know how to handle. So you need something between this job here, which has a very universal gates, and some observables here, which are also very general and not only Z gates. And so for this, a nice way in a programmatic fashion to see things is to see VQE as something that receives a job with a variational circuit and an observable whose energy we want to minimize, and that is going to return the least or the smallest value of this energy. So that the role of VQE is actually just to send some circuits on the right here, receive some results, and based on the result, doing some gradient updates or the projective updates we heard about yesterday in Francesco's talk. So that's basically what VQE does, what QPE does. Just send jobs here and receive, and based on the energy, do something. And we're missing here in the middle what we call compilers, which are basically things that are going to take into account the connectivity, the gate set, let's say the qubit ordering, that could also optimize the depth of the circuit, given the properties of the QPU on the right. And then the last thing here is that the circuit here is now optimized, but the observable is not something you can compute because it has X, Z, Y. And so here you should split the observable in a clever way by grouping Pauli operators or using the methods we heard about this week. And it turns out that all this holds in this plugin / QPU stack. So you just have to stack these modules one on the other and not use a black box approach. So you can really use what you want for your Kubernetes. And so here, okay, this is very boring to show code, but basically what I'm going to argue is that you can do very simply in one page of code for really a very complicated LIH molecule. So you start with the H and G, so 1 and 2 qubit, 1 and 2 body orbitals. Integrals, you construct your cluster operators, you go to Jordan-Wigner or other bases. Then you construct your ansatz. So basically on the cluster operators here that you tractorize here. So you just take your cluster operators and you use a tractorization routine, but you could replace this box by whatever method you like. And at the end, you get a job. And this job contains a variational circuit and a Hamiltonian. And then the final part is really easy. You load a plugin that is going to do the optimization. So here we're using a SciPy, but it could be SPSA that we heard about in the last talk, or particle swarm optimization or natural gradient. And then we construct a stack as a box optimizer SciPy, and here as an emulator. So I don't need the boxes in the middle because it's an emulator, so it understands any gates. And then I just submit the job and get the final result, which has the value of the energy. And if I want to use IBM, say IBM's QPU, I only have to replace the green box here by a backend to QPU where I give my IBM token and I select whatever machine I want to have access to. And I just replace this green box by an actual QPU and it still works the same. And I'm going and this is also available freely in something called MyQLM. And in the bigger server where we can do really large simulations, which is called QLM, we have additionally high performance noiseless simulation, hardware models, and noisy simulations. And I think I'm going to close the talk on this. Thank you. Yeah. Yeah. Actually it's a very good point, because if you read the original paper of Levin on natural orbitals, they say the optimal basis of state determinants. When you look at the math, you look at what is the optimal basis for instance, to minimize the Feynman entropy of the distribution. It's actually not the NO basis. The NO basis is for two particles in the function. If you want to go to larger number of particles, it no longer holds. But of course, then if you want to optimize, you need to have access to the 2RDN. So there's a hierarchy. So we're not saying that it's optimal. We're saying it helps at a low cost. And of course, using the one known or using optimizing on another quantum number called seniority, you will get better results.
With seniority, okay.
Yeah, there are some works too that try to optimize a different number, but for seniority, if I'm not mistaken, we have to have access to the 2RDN. So we have to pay M4. But so it's true that the optimality criterion here, I believe, on the fourth, because it's what is more or less what people say, but in practice, real quantum chemists, so not like me, they know that there are better things to do than M4. Okay. We're just saying it's a cheap way to improve quite drastically the results. So that's what. So in one iteration you already go there, and two iterations you already see.
Can I ask another question? The EQE complexity. So you said it's n shots, times an iteration, times and terms, which I agree. In this, we never consider the gate complexity.
Yeah. Yes, we should. So here, in principle, there times the time it takes to run the quantum circuits.
Okay.
Of course, yeah. So you're right. We should take this into account, and this is why we sort of take it into account on the epsilon intrinsic, because that's to shorten the circuit depth, more noise. So, and also, I must say that these are not independent parameters, as we learned, I think, 2 days ago. When you could also put the terms in a better way, and then try to adapt the number of shots to the coefficients in the lambda case. So there's lots of, so it's all entangled in a way, those parameters.
Okay, thank you.
So here you already mentioned whether we do active space selection or not. So here, no, we don't do active space selection. So we compute the full RDN, the full 1 RDN for all orbitals, which in our case is not a big deal because we're not dealing with a huge molecule. But anyway, we do the only n squared orbitals. And then we diagonalize this guy, which is a polynomial operation. And then we do it. Yeah. So I think the best way to go is first do your Hartree Fock or something simple on a classical computer. Look at the NOs, throw away the ones which are easy, so empty or occupied orbitals, and keep only the hard ones, so the correlated ones, and then do this just on the active space. So here I did something quite simple, but of course, if you want to beat, I mean, to really handle a real problem for active space. No, I mean we have tried and we have done computations for chemistry and for LIH and stuff like that. That's in the paper with but yeah, for this analyzation we didn't do both at the same time. In order to single out what analyzation does with respect to something.
The other question.
This is going to be obviously some totally wrong. I would say that we definitely know primary correlation of the basis is a localized basis. So like we see the annual basis.
No, I think that's all good. I think, yeah.
Like there's a crossover point where a localized basis makes sense. These computing that's you're not in that range.
Yes, so what is not clear to me is how, so where do we switch criterion, or so is there a way where we could find an optimal basis, but in which way to define it is not clear to me.
No, it's well, localized basis makes sense when interactions start to decay quickly because of distance. Yeah, you don't have this. So.
Yeah, like the orbitals.
Yeah.
I have just one quick question on the advantage. So you said something at the end, so about error correction, fault tolerance. So did you say basically that in the, as long as the moving machine is disk, there will not be quantum advantage with this method realistically? Is that kind of what you're?
So what I'm arguing is that for this method that I presented, below a certain level, the price to pay for the classical method is too hard. And so, and the conjecture or the idea is that maybe this value beyond which or below which basically the classical methods cannot catch up may also be this a similar value as the one where you could try to start correcting actually. But
is a like a hunch, or how should I say, an intuition?
There's nothing precise. And I think today, so this year there's been results at ETH, at Google, and at Continuum as well, of first quantum error correction results, where by gaining a little bit with respect to what they had before, they start roughly having logical quality, which is
they start. Yes. And just a quick question still. So you need a lot of effort to get this but are there applications for this, or is this purely to demonstrate advantage?
So I think the application is so it may look artificial in a way, but it's so let's say it allows us, for instance, to say if to quantify what is the quality of today's quantum machines. And it tells us that if we can, with this classical method, reach, let's say, a score of 20, then it means that that's what Google or IBM or whoever should reach. So in a way, it's an exercise, but it tells you, roughly speaking, okay, we have a method today where if we want to solve 2 AUA, this works pretty well, and Google cannot match it.
If there are no further questions, let's get Thomas. And then the next talk is by Zoom.